A continuous monitoring test instrument for hydroelectric turbines will not only save money by detecting efficiency robbing equipment problems early on that otherwise might go undetected for years, will also provide individual unit efficiency performance data that is essential for any comprehensive water-to-wire hydropower joint load optimization program. The following is a real-world case study that demonstrates the savings that can be obtained by use of a continuous efficiency monitor to identify small problems before they become big, expensive problems. The subject powerhouse has a common penstock with a time-of-flight absolute value flow meter located upstream of a split in the penstock that supplies two Francis-type turbines. After the manufacturer refurbished both generating units at the subject powerhouse in 2007, efficiency performance tests were conducted at the turbine's design head of 125.7 feet gross head to verify contract guarantees, calibrate the Winter Kennedy taps to absolute values, and establish a performance standard for subsequent efficiency tests. Another index test was performed in 2009 when head was at 113 feet. 10% below design head. The purpose was to define flow and power tables for the units, but the index test showed up an unexpected problem. The affinity laws were used to adjust the data from 113 feet to 125.7 feet for comparison with the acceptance test result, and then were supposed to be stepped in 1-foot increments to prepare flow tables between the two actual test points. Test results showed that efficiency performance of the machine was significantly reduced, so farther testing was scheduled for when water levels got closer to the design head. A year later, when head had returned to a level closer to design head, 124 feet, which is 1.4% less than design head, a third index test was conducted for diagnostic purposes. A year after that, another test was conducted at 130 feet head, which is 3.4% above design head. From these data, it was observed that the design head, the head at which peak efficiency occurs, had shifted from 125.7 to 140 feet, and that maximum generator output at rated head had decreased by 2.5 megawatts. This apparent 13-foot head loss is approximately the suction head from the draft tube's expansion at rated flow, so the first diagnostic educated guess as to the cause of the problem was that air is leaking into the draft tube below the runner, defeating the draft tube's reclamation of the velocity energy in the water stream in the discharge. This could be caused by either a bad seal or stuck open vacuum breaker valve. From here it becomes a process of elimination to find the culprit. We do not know and may never learn the final solution, but the need for a continuous monitor was dramatically shown by this case study. Chance played a role in this. If there had not been an efficiency performance test in 2009 to prepare new flow tables, this problem might still not have been found and the waste continued unnoticed. The full impact of this problem will not be realized until the losses are put into dollars. This Excel spreadsheet was prepared to evaluate the losses associated with turbine inefficiencies. A copy can be downloaded from a link in the cover letter to this video. A few assumptions must be made in the absence of actual generated power figures to put a dollar value on this loss. To show how the spreadsheet works, let's assume the turbine has been operated 60% of the time at what should be its peak efficiency point of 36 megawatts, where the preceding real-world efficiency performance analysis has shown a 6% efficiency reduction that has been wasting 2.16 megawatts valued at $64.80 per hour for over 3 years. This spreadsheet emphasizes the value of constant hydroelectric monitoring. This estimate shows the annual loss to exceed $340,589. Over the 3 years that the problem has been known to exist, from 2009 and before until 2012, total estimated losses exceed $1,021,766 since it was first detected in 2009 and finally diagnosed and corrected in 2012. An index test box costing about $50,000, installed and operating as a continuous monitor in this power plant, would have not only detected this problem immediately so that it could have been corrected early on, the real-world data would populate the flow tables with more relevant information to improve the data for subsequent condition monitoring. The potential gains, or avoided losses, demonstrated by this analysis show how an index test box would have paid for itself in less than 2 months in this case study by saving over $1 million in 3 years. Having an index test box permanently installed as a continuous efficiency monitor would be like running an index test on these units every single day to catch small problems before they become big, expensive problems. Oh yeah, did I mention that a single index test box can monitor more than one unit? An index test box continuous efficiency monitor is an off-the-shelf IBM PC or cloned computer with a National Instruments analog to digital input-output board and the actuation test equipment index test box Visual Basic program for testing hydroelectric turbines. The index test box program was written to allow multitasking with any other Windows-based program normally found on a typical office workstation computer.